All right, guys, so welcome to 2.8 angle proofs. Just to let you know, if this video runs a little long, I do apologize, but that's because the assignment in class, we might stop if the day's running long, and then we finish it Friday, and they just have a work day on some practice. So there won't be a video for tomorrow. So if this runs a little long, it's because it's kind of like the video for both. And then tomorrow is just a practice page of proofs. So this is on Canvas for you to print. In fact, if you are able to print it, I would probably recommend doing that to follow along. Otherwise, it's okay to go along with this. So the two warm-ups, if you want to look at the file, it's one, I want you to try writing a baby proof. It's kind of like a small proof like the ones we did for segments the other day. I just want you to try to create one out of your head. Not like one of the crazy ones, but like one of the more regular ones where it's just kind of put the segment addition postulate, plug in the things, and it's like see what you have to do to finish. And then there's a second one that has been done for you. Again, not something I would want you necessarily be able to create from scratch, but I want you to go in and give all of the explanation. So if you want to just take a minute to do that, pause this video and go and look at that, and then I'll go over the answers. So of course, we always start our proofs with our given. So AC is 25, BC is 8. That is our given. For this type of a problem, I'm typically going to do segment addition, which is part plus part equals whole. So in this case, AB plus BC does equal AC, and that is sort of a postulate called segment addition, basically it's the fact that we're allowed to do that. I then replace what I know, so I don't know what AB is yet. BC is 8, and AC is 25, so that is simply a substitution step. Then if I subtract 8 to the other side, I get that AB is equal to 17. That would be a subtraction, POE. And notice I try to use enough of the letters in the word substitution that I can tell the substitution and subtraction, because you should always be putting POE on the add, subtract, multiply, divide algebra steps anyway, but it helps make sure that you see those as different. And of course, that's how the answer would look. I didn't have to spin it around with symmetric or anything, so that was that one. And then here were the statements that went along with this one. So if you want to kind of check your work on that, of course you got my givens, my segment addition. They then replace all that algebra. They simplified by kind of combining like terms over here. Then they subtracted, divided, and got to x equals 4, and they felt like that was important. The goal of this question is to prove if these two segments are really congruent to each other. So they said, well, now that I know what x is, I went ahead and plugged it into both of these things separately. So you kind of see they're doing it twice. It's here I'm plugging it in, getting 13. Here I'm plugging it in, I'm getting 13. And this can be a substitution step, because if AB is 13 and BC is 13, then I can literally replace this 13 with BC, which is what they did there. And of course, if they're equal, we understand that means they can be written as congruent, and there's our definition of congruent sign coming back. Okay, so again, all that was just kind of warm up and bring back a lot of the types of properties we saw without having to make you do like a crazy one. So today we're introducing what's called the angle addition postulate, and just like segments, it's the general idea that this smaller angle plus this part of the angle will add up to the whole thing, as far as their measurements will add up to each other. So there's a little definition of that, basically, depending on what letters are in the question, but again, it's just saying that. So there are some common, I would call these, I guess, theorems. They're just generally things that we're going to write a lot. I'm talking loud because I left my paper over here that I had some of these written down on, and I was trying to just make sure I didn't forget to say something really obvious. Okay, cool, got that handy. So what's considered the supplement theorem? Like, we know that supplementary angles add up to 180. So kind of like how we had segment addition, where you could do like blank plus blank equals the whole amount. Supplement theorem is basically saying that the measure of, let's say, a particular angle plus the measure of maybe a different angle will add up to 180. So the fact that we know that, if let's say I'm given that there's supplementary, or maybe I see something that lets me know it's supplementary, that this is an allowed statement that gives me some places to plug stuff in. Usually what we would write as the step is you can literally just write definition of supplementary. Something that you'll notice is depending on sort of the style of the person that's writing, we also can write everything in if-then statements. So for example, what really is the definition of supplementary? It's basically saying if, and here's how I would shortcut this, is if there's supplementary, then 180. Like I know that there's supplementary, then they add up to 180. That's me super shortcutting, like if the angles are supplementary, then their measures add up to 180. I'm basically shortcutting that sentence. But sometimes it depends, it could be the other way around. Like maybe I know that they add up to 180. So if they add up to 180, then I know I'm allowed to call those supplementary. So sometimes the if then will physically be in the other direction depending what way you're going. For example, that definition of congruent sign, I of course write like definition of congruent, but like for just a fast example I would tell my class is I could write this as if equal sign then congruent. Like that's another if-then type form to write that, because we're going to use a lot of if-thens in our statements. So sometimes if you don't remember, was this one definition of, but you can give me the if-then like as a property, that's good. But notice if the original problem started with congruent and then I needed to go to equal signs, well now I'm going to say if congruent then equal. So the direction matters depending on which direction you're going, but the word's definition of congruent is kind of the fact that you're allowed to do that in either direction. But I just wanted to point that out. So if you ever see me write something in if-then form versus definition of, that sometimes that can be done that way, and like not to worry. If you're ever on a proof and you just can't think of a line but you know why, try writing an if-then statement for it. All right. Complement theorem is literally the same thing, it's just when it equals 90. So I'm not going to waste your time writing that. Okay, what I wanted to talk about with vertical angles and linear pairs, and I have this little diagram so I can reference it here. So sometimes the question will say, hey, these are vertical angles. I'm like, well, great, they're vertical angles, given. And then I can talk about those being congruent. Other times I just see them and need to talk about them. And so if I need to identify them, literally in a proof I could say, let's say angle 1 and angle 3. So let's say I would say angle 1 and angle 3, and I usually shortcut things. So vertical angle, I'm like VA. So if you see me like right angle, like RA, like linear pair, LP. Like I'll do that a lot, so just kind of watch out for those. And this is when you definitely will just say definition of a vertical angle. When I see something, it's going to be definition of. Like I really can't think of a good if-then statement for this that doesn't involve a lot of like, if the angles are across from each other, then they're called vertical angle. Like this is a great like definition of. Like I'm gonna always write definition of vertical angle for that. Now, what do I know about that? Well, that means that the angles are congruent to each other. And so then this is what I tend to write as an if-then statement. I tend to write like if vertical angles, then they're congruent. And so the problem is I don't really want to call that also definition of vertical angle, because like I'm already using that to just see them, right? So I tend to reserve definition of 90% of the time for things I see and just need to write down. Okay. Now, let's say I needed to talk about their measures, right? Because it's kind of like last time, with congruent signs usually need to be put in equal signs. If my problem needs me to discuss their values being equal, well, now I'll change it to measure of that angle equals measure of this angle. And that, of course, it's the same definition of congruency sign. It's just that I can convert those. Just remember that in segments, we usually have that bar on top, and then this is like their distance. For angles, if I say like angle B, then it becomes measure angle B. So that's just kind of the similarity between those. The other one that I'll just write underneath this is for linear pairs. Let's say in a proof I need to observe linear pairs. And I say, well, these two make a line. Great. So we say angle 1, and I said what, angle 2, and I would put LP for linear pair. And I would say that is definition of what a linear pair looks like. So like I can tell that's a linear pair. And then this one sort of comes in a block of 3 a lot of times in a proof. When I see a linear pair, what that then lets me know, because I'm probably trying to get it to the fact that they add up to 180. So if those are a linear pair, then what that means is that angle 1 and angle 2 are also supplementary. And so my if-then statement for this is like, well, if they're a linear pair, then they are supplementary. Now, if they're a linear pair, they're also adjacent, right? There's other properties that may have been helpful, but for here, the part that's a property that I need is a supplementary piece, and that's why I'm using that. And then very likely, I'm going to then, now that I know they're supplementary, add this piece, that the measure of angle 1 plus the measure of angle 2 equals 180, definition of supplementary, or like I said, a different student might have said, if supplementary, then 180. Both of those are okay things to me. Like I said, definition of, I generally 90% of the time is just to identify things I see, but on occasion, something like that, like I'm also okay with that. But that's where I'm getting at, is if you're not sure and you feel like you could write a short if-then statement that feels like it makes sense, there are times I will accept that. Okay, so that was just what I wanted to talk about, but I really wanted to get into some other, like, let's actually practice writing proofs, but I thought I wanted to sort of preview those and have you write those down so that they're kind of like mentally in your brain when we go to start using them. This is just straight out of the textbook. This is more like always, sometimes never style thinking, not necessarily things that we're going to use as a statement in a proof necessarily, but just the fact that when lines intersect each other and they're perpendicular, remember, a perpendicular line means the full line for forever. The full line for forever will always form 4 right angles. There's a theorem that says all right angles are congruent to each other. The idea is like, well, if they're all 90, then they have to all be the same size, you know, as far as like their opening. Perpendicular lines will form congruent adjacent angles. So angles that are right next to each other means adjacent, and because if all of these are 90, then the ones next to each other are congruent. If 2 angles are congruent and they're also supplementary, so if they add up to 180, but they are also the same as each other, that the only thing that's possible is for those to be right angles that are 90 degrees. And lastly, if I have 2 angles that are congruent, it's kind of the opposite of this. If they're congruent and they're making a linear pair, they are right angles. And the idea is that a linear pair means supplementary and they're congruent, so on and so forth. Now on your printed page, there's a proof on the side, I have it underneath, and I just wanted to randomly show like the proof of one of these steps just to show. So they basically want to say, if I know that these are a linear pair, then will they be right angles? So I just wanted to kind of show you this little quick proof. Again, the proof is done for us, we're just stating the reason. So they told me that they're 2 congruent angles. So I'm just using 7 and 8 because it's what the picture is using. So that's my given. Technically, it says in the question that they make a linear pair, so I would be comfortable with saying given as well. If they did not state that and I could see the picture, then that's where I would say definition of linear pair, because I can see it and maybe I need to talk about it. Because it's in the wording, I could argue this is a given, right? Because sometimes they're going to tell you something that you could have seen yourself, but you gave it to me. So here's that little 3 block I always talk about. Whenever you see the linear pair, it's likely going to be converted from, if it's a linear pair, then those are going to be supplementary to each other. And then the definition of supplementary angles, or like I said, if supplementary, then 180, and I'm kind of scribbling, that gets me to here. Now the next thing is measure of 7 equals measure of 8. You're like, oh, where's that coming from? That is literally coming from the original line, because I can't like substitute certain information. So this is that definition of congruent sign again, or now I'm okay with you writing that like if congruent, then equal, because I'm going to need that when I go to start replacing things. Because you told me they're the same size and shape each other, and this actually gives me the same looking M with the angle that I can start plugging things in. Now it looks like they took this line and literally replaced 8 with 7, which we know they can do with substitution. It looks like they then added those together like terms, so that's not an add step, that's just a simplify step that they combined what they were looking at. Then they divided both sides, so they did their little algebra to get that they're both 90. And so this isn't just like, oh, well, I could have done the same thing. This is probably saying, if measure of 7 is equal to measure of 8, and now I know measure of 7 is 90, I can also replace this measure of 7 with a measure of 8 and also write that statement down. So I would consider that a substitution step, that they took that 7 is equal to 8 and like replaced that here. Why do they need both of those statements? Because the question mentions that those two angles would be right angles, so I needed to see that both of them measure 90, and then notice I dropped the letter M here because it's the actual angles are right angles, and so that is, again, that definition of what we call a right angle is an angle with 90 degrees. Or if you're an if-then person, we would say if 90 degrees, then right angles. Again, that's really a shortcutted longer sentence. Like if the measure of an angle is 90 degrees, then that angle is a right angle, right? So again, definition of right angle is totally fine for me there. All right, next. And this is the part that, like I said, in class might run long. So I'm just gonna kind of talk through as many of them as we get through, and we'll just kind of like see how that goes. So this first one here says, given measure of 1 equals 20, given that measure of 2 equals 30, prove that the measure of ABC is 50. So they're basically saying, if this is 20 and this is 30, is the whole thing 50? Duh, right? But we're trying to teach you what steps look like, so we're practicing writing easy concepts with their steps. So of course my givens, measure of angle 1 is 20, measure of angle 2 is 30. If I can't fit them on one line like I did, great, I'm just gonna write given. I know that I'm gonna wanna add these together. So this is that angle addition, like we did segment addition, that says that the measures of angle 1 plus the measures of angle 2 will add up to the measure of the full thing. In this case, we're using A, B, C to describe that. That as a step is angle addition, just like I have segment addition. I'm expecting that I'm just going to plug those things in. So measure of angle 1 literally can go here is 20 plus 30 is equal to measure of angle ABC. That's a substitution step. I'll then just add that together to get 50 equals measure of angle ABC as a simplify step. And I would basically be done, except I do need to flip it around. And when I flip that around, the name for that is the symmetric property. Okay, so symmetric. All right, so let's just do some more and see how far we get. Here, I'm going to try to write this a little bit wider because I realized I had an issue with my spacing. So again, measure of angle 1 is 40, measure of angle 2 is 50. That's a given. Can I prove that ABC is a right angle? Well, the idea is, okay, yeah, 40 plus 50 is 90. If it adds up to 90, then that's a right angle just because that's what's called a right angle. So let's do that. We're going to need that same angle addition step. So the measure of angle 1 plus the measure of angle 2 adds up to the measure of, in this case, ABC. That is, again, my angle addition. And I'm going to substitute in that I know this is 40, plus I know this is 50. Is the measure of angle ABC, so it's substitution. Combine like terms to get 90. So combining like terms is simplify. And now that I know that the measure of this angle is 90, I can say, now notice I'm going to drop the letter M here. I'm going to write the angle ABC is right angle. And why do I know that? Definition of what we call a right angle, okay? Or if 90 degrees, then RA, okay? That's also how I could write that. All right, let's see a couple more. This one, they are giving me no picture, that's okay, but they're telling me that measure of angle 1 is 30 and that measure of angle 2 is 60. Can I prove that those are complementary angles? Well, the idea is that I know if I can add this together, 30 plus 60 is 90, and if two angles add up to 90, that means complementary. Great. The reason I picked this proof is we can't really do angle addition in the sense that angle addition is when I can physically see this angle plus this angle equals whole angle. For things to be supplementary or complementary, they don't have to be adjacent and next to each other. They could be some random angle, and they just happen to add up to 90 when I look at their values or their measures. So this problem becomes a little bit more interesting. Of course, that's my given, because I cannot write angle addition when I go to add these. But so think about, like, again, our systems problems where I took a row and I literally just stacked and added them, like all the stuff on the left equals all the stuff on the right added up, that I'm allowed to do that. That's kind of what I'm doing here. Like this line and this line right under it, if I were to just add those two rows together, it would look like the left, measure of angle 1 plus measure of angle 2, would equal on this right-hand side 30 plus 60. So that is what we've been calling equation addition, but just generally that's kind of what's going on. So I've also seen people do, if that equation addition is weird, I've seen another way to do this is to physically write, like take measure of angle 1 equals 30 and then do a plus measure of angle 2 as a add POE, and then I can substitute the 60. So you can go that route too. I think I go this route because it's one step instead of two, but again, that's not incorrect. At this point, I simplify that, so the measure of angle 1 plus the measure of angle 2 adds up to 90 based off me simplifying that math. And if two angles are adding up to 90, then that means that those angles, again, I'm dropping the M, I'm just referring to the angles themselves. Angle 1 and angle 2 are complementary, and that is the definition of what a complementary angle is. Okay, another one. And in class, we might have gotten about here, but we're going to keep going just with all on one video for you. This one, they're telling me that the measure of angle 2 is 60. So if that's 60, then this one would be 120. And we know that's because it makes a line, makes 180. If that's 60, this is the rest. Right? We know that, so how do we write that? So I know this. I could potentially do this as like an angle addition, but they didn't really give me letters for me to call that an angle. So this is just where I'm going to go in and say I see linear pairs. And if I see linear pairs, notice I'm not using M, I'm just talking about the actual angle. The actual angle 1 and the actual angle 2, those are a linear pair. Definition of what we call a linear pair when I see them. And this is that 3 block, where now I'm going to say that that means those two angles are supplementary, because if I have a linear pair, then one of their properties is that they are supplementary. And if they're supplementary, then their measures, that's where the M's come in, add up to 180. And that again is like definition of supplementary, or if supplementary, then 180. At this point, I'm expecting to substitute that the measure of angle 2 is 60. So measure of angle 1 plus 60 equals 180. That is a substitution step. And then when I subtract that over, measure of angle 1 is 120. That is a subtraction property of equality, and that takes me to the proof. Okay, so again, I started with, I don't say going in order of difficulty, but just kind of showing you ones that do just use the angle addition step, substitute, see what you need to do. Angle addition step, substitute, see what you need to do. Here, had a sort of a weird adding step, and here's where I need to visually look at and identify linear pairs. This does happen quite a bit in a lot of the math that we do, so I'm going to do like a second one that does that, and this one I think is not so bad. It says given the figure, so I'm just going to write figure and given, but sometimes if they just like, here's the picture, prove this, you're like, it means all the information's in the picture, which means I have to be able to say what I see to somebody, because right now, if I'm trying to prove something, somebody has no idea what's even happening. So I'm like, okay, guys, I notice over there, I see a linear pair. I see, here's that 3 block, I see that there's an angle 1, and an angle 2, and I see that those are linear pairs because it's definitional linear pair. We have talked about that being a line. That's what they're called. And then that one of those properties means that angle 1 and angle 2 are going to be supplementary, because if linear pair, then supplementary, and then that takes me to that measure of angle 1 plus measure of angle 2 will add up to 180. Definition of what supplementary angles are, or if supplementary, then 180. Well, now I get all the way here. What are we trying to prove? That measure of angle 1 equals 180 minus that. So it looks like if I just minus this to the other side, I get that. Measure of angle 1 is 180 minus measure of angle 2. That would be a subtraction property of equality, and it looks like what they want, so I just stopped what I'm doing. Okay, if they gave me information, I would be able to plug that in. This last one, I wanted to show one that has this little perpendicular symbol in it. This is probably the longest one of this set of 6, so it's just a good one to see. And for last one, and I'm going to get this in under 30 minutes, cha-ching. Okay, so it tells me that AB is perpendicular to BC, and I also know that measure of angle 1 equals 20. These are both my givens. If you can fit them on one line, cool. The goal is to prove that measure of angle 2 is 70 if I know this one's 20. And if they're perpendicular, that means I have right angles that are 90 degrees, then I can subtract them, like all that fun stuff. So let me think about the order I would personally do this in, because sometimes there's more than one way to think about it. Oops. Dropping my pen here. So one of the things I'm going to mention is that angle ABC is a right angle. So this is kind of like when I say angle 1 and angle 2 are a linear pair. Like, I know that angle ABC is a right angle, but why do you know that? You can't just like look at it and say I know that. I know that because of this perpendicular symbol. So this is an example of like definition of the perpendicular symbol, or that little always sometimes never definition stuff I pointed out, where it was like if they're perpendicular, it's going to create 4 right angles. So this really could also be like if perpendicular symbol, then RA, right? That would be an appropriate like definition of that symbol, means I have right angles. If this is a right angle, I know I'm going to need to use the measure. So that means that the measure of angle ABC is 90. And that would be a definition of right angle. Okay, but again, if you are more comfortable with your if-then statements, you would have said here, okay, well, if perpendicular, then I know that's a right angle. And if it's a right angle, then I know that it's 90. So some students, even though it might feel like a little more writing, actually like the if-thens because it feels like they can like say their logic in order. But the definition of are equally appropriate in certain situations. All right, what else can I know? I don't have anything that says measure of angle 1, like physically for me to stick the 20 in. This is where that angle addition is going to get that for me. So the angle addition, I can talk about the measure of angle 1 plus the measure of angle 2 will add up to the full thing. So that's where I'm going to get a statement from the picture that lets me now plug in some of these things I also wrote down. And I'll be honest with you, I could have started with this angle addition and then use that later, but these things all kind of had to happen at some point right now so that I can now do my final steps, which is replacing measure of angle 1 with a 20 plus measure of angle 2. Measure of angle ABC, I have, so not just ABC, but measure of ABC equals 90. So this is just me substituting things all over the place. Final step, subtract 20 to the other side, and I get 70 from a subtraction property of equality. That is a lot to digest, but I'm hoping like the more you see it, the less weird it gets. The homework that goes with this, again, it's not actually a proof. This one is in the little packet again, so if you want to like scroll and find those pages and print those pages out if you didn't print the whole packet out. But I'm only asking you to do 1 through 15. I think if you look, it actually goes 1 through 18. 1 through 15 is plenty again. And just like the segments, I don't need you to write proofs. You're not writing proofs, you're just doing them. And some of them are pretty quick because it's just kind of like what the numbers are doing. And as algebra gets involved, I would expect to see something like, did you know these were equal to each other? Did you know they added up to 180 or 90? And then kind of finishing out your algebra from there. Okay, tomorrow there will not be a video. Tomorrow I'm going to just post a set of baby proofs. In fact, they're in this packet, so for those of you who did that, and be careful, this one says beginning proofs, it's not that. It's a page that says baby proofs number 1. It's got like 8 problems. A lot of the stuff we've been looking at between the segment day and the angle day answer all of those. So you can pretty much do those with only the steps that we've already seen. Okay, again, one last reminder, your chapter worksheets due on Tuesday, so definitely be coming on to the calls if you want to ask about those or go over any of those answers. Okay, have a good day, you guys.